All right, the question was posed in an earlier lecture that could we not make our time constants, our delays, with inductors as well as instead of capacitors? And the answer is absolutely yes. We can create a time constant with an inductor as much as we would with a capacitor in this manner. But I just wanted to kind of point out that so when the capacitor, we got one time constant equals RC and 5 time constants for 5 RC. To make a 5-second delay, we would say that we actually want to do a one time constant would be 1 second. Okay, 1 second here. And we have 1.5 k ohm resistor. We'll just put a modest little resistor in here. And 1.5 k times x, which is a capacitance, is equal to 1 second. So 1 second divided by 1.5 k is equal to our capacitance. And as you can see, 666.7 microfarads would be our x. And we're talking about a little capacitor here, okay? So that makes us very happy, makes a nice little small space. But the question is, how big, what size of an inductor would we need to make the same time delay? Well, we're going to go ahead and do the same thing. We're going to say 1 second is equal to our time delay, which is going to be equal to our x divided by our 1.5 k ohms, excuse me. And as we will see, that 1 second times 1.5 k ohms is equal to x. Well, wait a minute. This is 1,500 henries is what we need for x. Now, folks, that's a pretty good sized inductor. Now, it may not seem like, like a huge amount, but 1,500 or 1.5 k henries is a really good size inductor. So, how big of an inductor is? Now, this is where we're going to talk about the permeability of air. Was one. Remember we talked about that? And we'll talk about iron also. We're going to talk about an iron value, which is about 200,000, okay, times the relative permeability of 1.256 E minus 6 here. 1.256 e to minus 6. Now that's going to be the absolute permeability of our air, or as times is going to be the absolute permeability of either one of those. Now our formula would say that 1,500 henries is equal to that value of 1 times 1.256 e minus 6 times the number of turns squared. In this case, we'll just do a modest number of 1,000. We're going to keep that the same for both of them, times the area, which is what we're going to look for, and the length. Now let's keep the length be modest, and let's make it probably 0.1 meters. We're always going to keep this thing in meters, and that's that's actually 10 centimeters, or out there. So at this size, with this value, solving for area, and then taking the area and dividing by pi, we will get the actual radius squared. And finding out the overall radius squared of this thing, we're actually talking about a diameter of 12 meters, approximately 12 meters. Okay, so it's 10 centimeters wide, 1,000 here, but that's 12. Folks, this is 36 feet, over 36 feet. Using the same thing for iron, what we'll find out is that it's 2.75 centimeters, but that's still almost an inch in diameter. Big difference between that and that capacitor.